Good morning. I'm doing this video to address an article that I was the lead author on, along with my father and business partner Brian Allred, that was published in July 2025, Concord International. Now, we intended to kind of shake things up a little bit with this article. That was the point. But unfortunately, it got shaken up in ways that we didn't intend, and that's kind of what I want to address here. My own criticism of myself may have been that I tried to pack too many things into one article of what was happening, or what we wanted to address. Anyway, the article is Understanding the Mysterious Overstrength of Post-Tension Flexural Members. Have we been missing something? You got to do something catchy if you want anybody to read your articles. So, what we were trying to do, first of all, is address the fact that university testing, in whatever decade it was done in, seems to always come up with or show that post-tension floor systems have much more capacity than they were designed to have. That the factored loads used in the design create a system that when tested, the test values exceed that sometimes dramatically. So that's one of the things we wanted to address. And then the second thing was addressing restraint. Now, you may not realize that reading the title of the article, but what we're trying to do is say that, we have all this test data that's really off the charts in capacity, but it's in completely unrestrained vacuum systems. And we, particularly in California, myself, my dad, Brian, we have all designed millions of square feet of post-tensioned one-way slabs, two-way slabs, and beams. We've also all taught this, so we feel qualified to write an article about it. But we've also, being in California, we have heavily restrained systems, floor systems. We have to. We don't have any choice. We have so much seismic force that we have to deal with that we have to put in a system that restrains the post-tension. We don't want to, but that's what happens. So this article is trying to address a lot of things. And like I said, it struck chords that we didn't intend to strike. So that's what I'm going to talk about today. So this figure was right off the bat in the article, and unfortunately this is what many people just couldn't get past. They really never got to the point that we were trying to make. They got caught up here, and it's my fault. It's my fault. So here are two different, I guess there should be a B down here, two different scenarios. One, I'll start with the second one. One is what we assume all the time, that we have a pre-compression force in the system. It makes its way to here. This is the same pre-compression force, and that's part of the issue we're going to discuss. In this scenario, those are the same forces. What we were trying to address was what happens when you have a restrained system, when the pre-compression force doesn't get into the floor system. And this is, I don't know if this is a crude way. For some reason, having a buttress seemed to bother people, and they focused on the buttress too, which I could have just drawn a wall and tried to show this some other way, but people got caught up in the fact that I didn't have a moment down here and didn't have a reaction, the soil pressure, and kind of got off track right off the bat. But that wasn't the point. One way or another, the pre-compression force doesn't get into the system. That's the point. And we drew a section cut that has a compression force in it. Now, what should have been obvious is that this compression force is not the pre-compression force, because the whole point of this was that the pre-compression force is assumed to be zero. It didn't get to the system. So that has to be another compression force. It has to be a compression force that's developed some other way or some other mechanism. And that's where this whole thing kind of came to a grinding halt. Was I got email after email and free body diagrams from people saying that I don't understand statics, that this can't be there if this isn't in the system. That's our fundamental disagreement. I wish I would have spent time discussing how we drew a compressive force that's not the pre-compression force and where that may have come from. So that's what I'm talking about today. But see, I think part of the problem is my dad, Brian, and I, we all work in California and always have. We know we have restraint. Sometimes we have significant restraint in our own buildings. We've certainly seen other people's buildings that have serious restraint. We get the phone calls, particularly my father, over the years when somebody's building has serious restraint cracks. And it's led to load testing. Over decades, there have been many load tests. Unfortunately, a lot of those load tests were in lawsuits, so getting the data is difficult. But I can state this, and my father and Brian too, I'll speak for them. Not one of us or anybody I've ever met is aware of a building, an actual building, that had concerns about restraint, cracking, and strength that got tested that didn't pass. They've all passed. They always pass. They have strength. Now, how do we explain that strength? That's what we're going to talk about today. But it's always been a given, or at least I thought it was a given, that PTI publishes and has always in one of the documents or another over decades stated that restraint to shortening cracks in slabs do not have a significant effect on ultimate strength of the section or factor of safety against failure. That's published. That's what we thought we all understood. I mean, I've taken that, I know that to be true because our own buildings are sometimes severely restrained. I'll show you one of them in a minute. And they always stand up. They do more than stand up. They get overloaded. I'm going to show you pictures of that too. And they always do fine. So I guess I just didn't think it was a problem to state that there's a mechanism that must be holding up these slabs, one-way, two-way beams, when the pre-compression isn't there. But that didn't go over so well for a lot of people. But remember, we think as post-tensioners, we believe this. And nobody's really challenged that. So, but I've learned, no, that's not the case. There are plenty of people that think we don't have any capacity, and I mean zero if we have a seriously restrained floor system. So this is not the given that we thought it was. Okay. Well, the responses I got back, and I'm glad I got, most of them were very respectful, and most just thought I didn't understand statics and nicely stated that, and that's okay. One was fairly aggressive, and I didn't really appreciate that. But anyway, when I got into a dialogue with a whole bunch of various people that sent me their free body diagrams and their opinions, some of them said, well, restraint's not really an issue. You just think it's an issue. And I thought, oh, really? Okay. And those statements came from people who don't practice and are not the engineer of record on buildings in California. So I said, well, here's a building right now that we are designing. Brian and I are designing this building. It actually has to satisfy the next code, which we've learned about a 30 to 40% hit increase in seismic forces. I mean, we never go backwards. So in California, it just keeps getting worse for us. We keep having to provide more seismic system. And by the way, Brian and I my dad will not design a system, a flat plate system that has moment frames. So we always have shear walls. The reason we don't is we learned in the Northridge earthquake, that when a building moves too much, it creates serious punching shear problems. So we are trying to minimize lateral displacements during earthquakes. And so you're kind of stuck with shear walls. And shear walls are great, I mean, they're great. But when you have so many of them, you're going to end up restraining portions of your building. We expect significant restraint here, and we expect it here and here too. So anyway, we think it's real. And in fact, that building hasn't even been built yet. And I can tell you, I'm going to go out and see a crack that looks something like this, maybe fairly regularly. Now, our system that I just showed you was a flat plate system. This system has beams, but it really doesn't make a difference. This is a big shear wall down here. It's restraining the system, and at some point from the edge of the shear wall, you will come in and start getting these cracks. And those of us in California know they exist, know they're going to exist. We have various ways of addressing them, and I'm going to show that to you in a minute. We try to do it with bonded reinforcement in the slab systems. I'm sure everybody addresses it partly that way too, but what's funny is that because we do a lot of we do plan checking for various cities in California, we do a lot of post-tension concrete peer reviews for the California State University and for the University of California, so we get to see other people's drawings a lot. And I just pulled from 3 different California structural engineering firms, all highly respected. I respect them. I promise you that California engineers know that we have restraint. And they put it on their drawings. Here's one. I won't read you all of this, but concrete cracks. That just comes right out of the general notes. I like it. We don't use that, but concrete crack section explained. Here's another one that we see a lot in California. They start actually estimating the feet of cracks per square feet of slab, and tell the owner should reserve funds for a maintenance program that's going to take place 2 years. It's going to go on for 2 years, and that's a correct number, by the way. Again, those of us in California dealing with restraints and cracks and things like that, we know that this happens over a 2-year period. It's not a 30-day period. It's not a 45-day open pour strip period or 60 days. It's 2 years that it really is. And the contractor, they're told, needs to epoxy or budget so much epoxy. These are notes that California engineers have come up with. Another one, routing and sealing of cracks. It's in the general notes that they're going to have to do this. And these are all post-tension concrete buildings, all post-tension concrete decks these notes come from. These people have decided it's industry standard, which I don't know if that's the case, but they think so. So the owner shall be credited if the allowance isn't all used. I love when those things are stated too. But anyway, the point is, in California, it's not theoretical. Please don't tell us that we don't really have restraint. We've just imagined it. We know it's true. We know we're going to have it. And everybody deals with it in their own way. So one thing I want to point out, and just put this one out there, there are many, many tests that have been done in situ, actual buildings that had concerns about restraint. They got tested. Like I said before, every single one that I have ever heard of passed the load test. Post-tensioning is absolutely amazing, but the fundamental reason that they were tested was because there was concern that so much restraint had happened, there's so much cracking, that there just wasn't any pre-compression in the system. Or for most of the system there wasn't. So it needed to be tested, and it always passes. So my point was, we seem to all believe, I want to go back, if you believe these statements, then you believe that there is a mechanism that is resisting this load that doesn't include the pre-compression, that this compressive force is not the pre-compression force, but somehow, some way, another mechanism is developed. If you believe that post-tension buildings under restraint are not going to fail, that they will stand, which they have for decades and decades, no one's aware of one that has fallen because of restraint. That assumes all the tendons are healthy. All the tendons remain stressed throughout the system. Talk about corrosion and other things, then we're talking about a different topic. But when all the tendons are good, they're stressed, remain stressed throughout the system. The only thing that's been lost is the pre-compression in the concrete due to restraint. I thought it was pretty clear that we believed this to be a fact, and surprisingly, we don't believe this to be a fact, or many people don't. In fact, I got so many free body diagrams sent to me that just said no. When you lose pre-compression, you have no flexural moment capacity whatsoever. And I said, really? That's interesting. I'm going to show that in a minute. But that would mean that we would have a failure a week in California, and we've never had one. So something is not aligning. Something is not adding up. So, again, my regret in that article was just stating that was a fact, that some type of mechanism would develop that would create that compression force that wasn't the pre-compression force. That I should have spent half the article on that point. So here we go. If we think the pre-compression force has to be this force, then when you have a bunch of restraint existing somewhere between the end of the building where the pre-compression force gets applied and where you're looking at it, maybe 125 feet in, if this goes to zero, a whole bunch of people sent me their pre-body diagrams saying, well, the moment capacity is zero. And that would be true if we had no other source of compression, if no other mechanism could develop. But again, kind of the frustration for me was that we state that we already believe that loss of pre-compression does not result in loss of strength. Those statements are made. Those statements are said all the time at ACI and PTI conferences and published in documents. And we tell that to owners. So it was a surprise to me how many people actually don't believe that and sent that to me. Okay. You end up with a pretty strange situation, by the way, when you have this section cut where you have the full tension force, you don't have any compression force. So that's a quagmire. That's a difficult thing to think about. So again, I would get back and forth with everybody who challenged this. I said, okay, then how do these buildings stand up, and why do they always stand up? If you've proven to me beyond a reasonable doubt that they can't stand up without that pre-compression force, why do they? So I get responses of, well, catenary. We believe catenary action actually kicks in, and that's the reason that these buildings don't fail, even though they theoretically should. Now remember, what is catenary action? The definition is structural mechanism where a beam or slab undergoing large deflections transitions from a bending and tension dominated behavior to basically hanging. It's basically just hanging like a net. Okay, I believe catenary action is real. Here's the problem that I have with this argument is that let's look at what we have to do for barrier cable, just to show that a barrier cable, one cable can resist a 2,000-pound load. For those of you who design barrier cable who have done it, it takes 3 cables to resist the 6,000-pound car load that we assume occurs. But to do that, now given the force in the strand isn't as great as it is in our regular buildings, but this example, which came out of PTI, needs a deflection of 19 inches to work. 19 inches. So that to me is the catenary effect. But yeah, I know this is an energy method that's developed, but still, the point is you need significant deflections of the post-tensioning to have the post-tensioning start to work in a catenary way. So my response to this is these pictures come from our buildings. As much as we try to convince these contractors not to overload the decks, and if you are going to load up these decks during construction, please reshore, they don't. And it's funny because they don't, because nobody believes in the strength of post-tensioning floor systems more than the people who build them. And that is the truth. They giggle at me when I get concerned. I look like a little old lady getting all nervous. And they say, these things are so strong. Oh, we do this all the time. Nothing to worry about. Here's one. This is our building. I walked up to it. Absolutely no reshores down below. And just staging all this material up on top. And I always say, please put in the reshores below. That's much more load than we ever designed for. And these things are usually 1 week old by the time we're looking at this. Look, the tendons haven't even been cut yet. They were just barely tensioned a few days ago, maybe a day ago. Doesn't matter. They start loading these things up. And like I said, the people who build these things have the most confidence in them. But look at this, too. This is a very significantly loaded deck. There's no deflection happening here. There is no deflection happening here. If our decks are really so strong because catenary effects kick in, you'd see deflections. You'd see serious deflections. And this one almost looks like it's still cambering up. So I struggle with the catenary action being the reason that we have so much strength. Here's another one. This was last week. I just happened to be out at one of our jobs. And by the way, this annoys me in the picture. The deck is not this thick. It actually has this curb on it, so the deck is actually about this thick. But anyway, this is our job. I'm walking it. It's the job's done. I got called out to look at one crack up at the top level, and I was walking up the building and realized they're staging for the apartments that are being built around and throwing everything in our parking structure. Not reshoring for that. But again, there's no deflection. These things just don't deflect. So here's what I think catenary action actually looks like. This is my one real experience with seeing what it really looks like. This was after a Northridge earthquake. There was a serious failure of a post-tensioned slab system supporting 2 or 3 levels of wood. Here's the shear and flexural failure. This was the top over a column. The thing had completely turned to rubble. The tendons were still in there and still working, if you can see them. This is what it looked like below. So this is catenary action. This is the concrete's not participating anymore. We don't have the Whitney stress block, tension, compression, couple, anymore resisting moment. We have the tendons holding this thing up as a big net. But this is what it looks like. This to me is what catenary action looks like. And as I state here, we don't measure it in inches, we measure it in feet. When catenary action really kicks in, the floor system will deflect almost down to the next floor, depending on the floor height. But this was coming down about 6 feet. Didn't quite make it to the other level. It really was standing using true catenary effect. Here's post-tension tendons right here. And they're going through here. But this drooped down about 6 feet. So my point is, you can say we have catenary action, and there may be a little bit of catenary action happening within our overloaded, restrained systems. But unless you see this pretty serious deflection, it's hard for me to believe that is really, the catenary action is really a big contributor. So not everybody agrees with me on this. So this is kind of my own opinion, but we develop our opinions based on our experiences, and that's part of my experience. So the next thing I was told, and this one drives me the most crazy. This one causes me to want to pull my hair out, because I've been teaching this for 15 years at UCLA, almost that long at Cal Poly, and taught other seminars and trying to explain what load balancing really is and how misunderstood that topic is. Just seems like I'm screaming in the wind sometimes. But let's do a quick review. So what some people told me was, well, we balance out some of the load, therefore we're, the post-tensioning, the system really only has to hold up the residual. And none of that's true. Okay, let's just real quickly go over what load balancing is. Load balancing was a terrific idea. T.Y. Lin wrote a paper in the 60s that said, hey, it's difficult to calculate the stresses in concrete, but he came up with a really slick, wonderful way to do it called load balancing using equivalent loads. But the problem with it is it's statically completely incorrect. And that's okay. I mean, T.Y. Lin understood that better than anybody. So don't use this for anything else other than stress calculations, but you can use it for stress calculations. So I've set up a real simple example. 60-foot beam. We don't know what this beam's made of. This beam could be post-tension. It could be rubber. It could be wood or steel or reinforced concrete. It doesn't matter. Statics is statics. And that sounds like such an obvious statement to make until you get into a discussion with somebody about post-tensioning. Then they don't really believe that statics is statics. But this is statics. 1 kip per foot, 60 total kips, 30 each side, and the reaction has to be shear diagram. This is a statically correct shear diagram, and that loading and shear diagram will create a static moment of 450 foot kips. There's no other alternative. There's no other argument to this. This is statics. It has to be this. Okay. So what's this load balancing argument, and how can we start saying that, well, maybe load balancing is taking some of the load, and therefore that's how a lot of this stands up, even in severely restrained structures? Makes no sense. Why? Okay, good. I love teaching this. I'm teaching it for a long time. I'll keep doing it. Statics says this isn't the case. So let's look at this. We can take, now it's become a post-tension concrete beam. Now I made it a post-tension concrete beam. But I didn't make it a non-static post-tension concrete beam. Static still applies to post-tensioning, despite what a lot of people seem to think. So I just threw some simple numbers, 225 kips of force, a 1 foot eccentricity, or drape. So we can pull this tendon out, and this is what T.Y. Lin said we can do. And it's genius. It's so powerful. And said, let's figure out the equivalent loads that are on this tendon to hold it in shape. And by the way, in this diagram, this is not the weight that's causing this. This is the stiffness of the concrete that's causing this. The tendons are being pulled. They're trying to straighten out. They're trying to straighten out. The stiffness of the concrete is not letting that happen. So it's creating an equivalent load, equivalently pushing down on those tendons as the tendons try to push up on the concrete. So in the tendon case, when we look at the tendon itself, when we pull it out, there is, under this scenario that I've created, a 0.5 kip per foot load. Equivalent load, not a real load, okay? Not an applied load. The only applied loads on this system are the 1 kip per foot that I've talked about in setting the problem up. So this isn't a real load. This is an equivalent load acting on the tendons. And then this is the diagram that everybody's aware of. And T.Y. Lin gave us such a powerful thing, but it gets so misused that I sometimes wonder if it was a great idea. It was a great idea, but you have to fully understand the idea. So this is now the concrete beam, just the concrete. We've taken the tendon out, and we're putting the loads that the tendon creates on the concrete. Everybody's aware of this diagram. Talk about it all the time. People sent it back to me. They completely forget about this diagram. And these two diagrams are happening simultaneously. One of them creates the other one. They have to go in unison. As this is getting stressed, it creates this and it creates this. And they are canceling each other out. They completely offset each other because statics is statics. This is happening inside this beam, but you don't know it. Tendons are pushing up on the concrete, concrete's pushing down on the tendons, they cancel each other out, nothing statically changes. What did T.Y. Lin say we could do though? Remember, our goal and what he was showing us how to do was calculate the flexural stresses in post-tension pre-stressed concrete beams. So what he said was, we have these two diagrams that cancel each other out. If we ignore this one, we just ignore it, we take it out, we put it off to the side. So we're not going to think about this diagram, we're only going to think about this. So it's statically incorrect to do that, but we can use that to actually calculate the stresses. So now, when we combine just one of the two equivalent load diagrams with the actual loading diagram, we get a fictitious system, one that's not statically correct, but we can use this to calculate stresses. Because now we're just looking at the concrete. We are just looking at the concrete as if the applied load and if this equivalent load was another real load. And again, what makes this not correct is we took one of the two diagrams that cancel each other out and we took it out of the system. We just eliminated it. So we are statically incorrect doing this. But when you do it, what happens? You end up with a net downward load, in my example, of 0.5 kips a foot. You end up, you have 30 kips coming up, but you have 15 kips coming down. So I don't need any more emails telling me I can't do statics. For a net 15 kip shear diagram, which is not the statically correct shear diagram, which then leads to a moment diagram that's actually half of the actual statically correct moment diagram. The statically correct moment diagram, so this is 450 foot kips, and it's correct. Using the equivalent loads, or using only half of the equivalent loads, we end up with a moment diagram that's not statically correct. But it turns out, as T.Y. Lin explained to us in the 1960s, this statically incorrect moment can be used in this equation and you will accurately get the stresses. You will get the true stresses in the concrete. So what an easy thing to do. Wow, did that become easy compared to your alternative of cutting sections and having the tendon in there and trying to come up with an eccentricity at every point balanced with an applied load. It's a very difficult problem. I gave that problem as homework number 2 at UCLA and Cal Poly for 15 years. So they had to do it both ways. But I think my students hopefully left with an understanding that while this reaction is not the reaction, this shear is not the shear, this moment's not the moment, the only thing we got that was correct were the stresses, the flexural stresses in the concrete. So that's the beauty of this. That's why it's so wonderful and so powerful. But it's the only thing that we can do with this very powerful method. We can't make statements like, well, we've balanced out half the load, so really we only have half the load to stand up, to make stand up. Those are crazy statements. Those are statements that lead people to believe that you can overbalance the system and the floor will lift up off the supports. Or if you overbalance all the floors, maybe the building lifts up and floats down the street a little bit. I mean, these are the things where you really get it wrong, and they're dangerous too, because if you start designing your beam or the supporting member for what you think the reactions actually are that aren't correct, I mean, that's a rabbit hole you just don't want to go down. So the point is, no, load balancing does not explain why our buildings are so strong and why they stand up even though we've had severe restraint. Please don't ever say that. at least within earshot of me, because that's frustrating for me. When we look at strength, we have to be looking at this 450 foot kips. We have to be looking at statically correct moments, statically correct shears, statically correct reactions. We have no choice. That load balancing method was very powerful just for checking flexural stresses. And you can also use it to check deflections. But other than that, you got to throw it away. You've got to toss it. Then don't get yourself confused that somehow we eliminated half the load. We didn't. You can't. Okay, so these were the discussions I had. Some people said catenary action, maybe a little bit, but really not enough to explain it to me, in my opinion. These are just my opinions. This is now just me. Load balancing is clearly not the explanation for this, and please don't think that, because you really don't understand what equivalent loads are or what T. Weiland was trying to teach us in the 60s. So what is it? How is this system standing up? Why can I put out an article and say that there's a compressive force being developed or a mechanism for holding up the building that doesn't include the pre-compression? And to me, again, I'm speaking only for myself, and I want this tested. I do. I am willing to put other people's money where my mouth is. And let's figure out how these systems are standing up when they don't have any significant pre-compression. I think, and I was taught, and I think we all know, again, you don't know what kind of beam this is. This could be a rubber beam. This could be a wood beam. This could be a steel beam. Be any kind of beam. But bending itself under load creates deflections and creates bending. And bending creates compression. This is the compressive zone of this beam in the span. This is the compressive zone of the beam over a support. There is a zone of compression. We can't say that without pre-compression in the system, we can never get compression. That's just, in my opinion, a false statement. And we wouldn't say that about any other material. And so if you have compression, you must have tension, and that's where our strands come in. That's where our post-tensioning tendons come in. So we've always believed that the tendons provide the tensile force in that section cut anywhere in there, and that we have a compressive force. I am not bothered by the fact that this compression force can be generated in more than one way, more than pre-compression. In fact, I'm going to say something really crazy. It's going to get me a lot more emails. I don't even think the pre-compression is the primary way that we resist flexure in these. I think bending is probably the primary source of compression. And if you have some pre-compression, that's great. But for those of us in California where we never have the full pre-compression, I guarantee that we may have some of it, we may have half of it, we may not have any of it in sections of the building, but it's never 100% all pre-compression. We have to believe that compression is generated some other way. And to me, the simple answer is just the bending itself that the slab or beam goes through. I have had a lot of trouble selling this, but it's still my belief. So bending, let's focus a little bit on bending and see. I believe we already believe, we as a group of post-tensioners believe that bending occurs and it does some amazing things. Let's talk about what we all believe. Okay, this is an unrestrained system. It's just like they build at the universities. No restraint whatsoever. Put a tension force, round numbers of 100 kips in the tendons. That same force is applied at the anchors in a compressive force into the system. So we balance, these are the same numbers. you know what's interesting is a lot of the people, because you have to, on an 8.5 by 11 piece of paper will draw this for me in their free body diagrams, and then 2 inches over show me what's happening in a section cut here. Probably should have made that a section cut. And that's easy to see and understand and believe when these things are inches apart on an 8.5 by 11 piece of paper. But I decided to draw this to scale because that's how it actually is. So here's an 8-inch slab, 210-foot long building, which is not a long building. Not a long building at all. We oftentimes are well north of 300 feet in one dimension. But let's pick this 30. I made some 30-foot bays. So this force is coming in over here, 100 kips. There's a tension force in the tendons going up and down. Of course, it's so tiny actually to scale, it's hard. It would be hard to draw. But then when we get to the point of interest, where we're looking at this is a positive moment location. What do we all believe? We believe this. We believe that this tension force actually increases. Why? How? By bending. We all believe that already. We say that we go to an FPS force. We put in an FSE force. But when it really matters, and when the system bends a lot and we have localized bending strains and stresses, we believe that we can increase this by the ratio of FPS over FSE. And in this particular case, in a slab, that's a 30 KSI increase. So if we start at 174 and we go to 204, that's a 17% increase. So we already, and that, how did that happen? That happened due to bending. That there's no other explanation. That we've all believed that, we're taught that, and I believe it. So bending by itself, just the act of bending, increased that tension force. Now, does that make it all the way back through the system to this anchor? Maybe, maybe not. I don't know. Not sure. That's another one of those debatable things. Does friction, this is 117 kips here, but it's 112 and it works its way down. I don't know. Probably something more like that, distributing down. I don't know, and it doesn't really matter to this discussion. But the point is, so if the tension force increased, then we believe, as a group of post-tensioners, that the compression force also increased. So, first of all, we started with this 100 kip force that everybody sends me in their free body diagram, but it actually increases just due to the act of bending. And not only did it increase by 17%, it moved itself up to where it needed to be to resist the moment. Now, we all believe that. We all draw Whitney stress blocks. Whitney stress block moved that compression force to the top in the positive moment regions, moved it to the bottom in the negative moment regions, and we're all fine with that. Nobody's sending me any emails saying that can't happen. So we just believe that bending, the simple act of bending, is so powerful that it can increase these forces and then move them to the most optimal place to resist the moment that's there. And I believe that. I do. I'm not being sarcastic or saying anything that I don't also believe. The only difference here is I've now become convinced that this compression force is going to develop itself whether or not it has pre-compression. But that all these other things are true, that this tension force will increase due to localized serious bending, causes an increase in strains, increase in stresses. But remember, this is straining over a long distance because it's unbonded. This is straining over a localized distance. We'll talk about that in a minute. Okay, so we take the same system, but now I'm going to put in these shear walls. These are really short shear walls. They're not very tall. I didn't have room in the picture to draw. I hope everyone's okay with that, but I didn't have room in the picture to draw a really tall shear wall. So I'm hoping everybody buys into this. So it's a restraining thing. Now we've got a seismic system in this 210-foot long building, some pretty long shear walls because we're in California and the new code is kicked in. So what now happens? Remember, we all believed everything I said previously, or if you didn't, then I don't know how you're designing post-tension concrete now. So now we restrain it. We start with that same 100 kips, this. We still believe that the tendon force, due to all this localized bending, will increase. How far this increase makes it all the way back, we don't know. Doesn't really matter to what we're doing right now. But the question is, if this restraint has taken out a substantial amount of that pre-compression, what is left? What gets here? And this is the discussion I've had with numerous people. Some say 0. Some say it's 0 and there's no other source of compression. Therefore, this slab collapses. It must. It must. If C is 0, I don't even know what we're really looking at because we're out of equilibrium. But I think logic tells us if that value is 0, it doesn't really matter that the tension force is still there in the tendon. We don't have moment capacity. Some people believe, well, the only compressive force that could develop due to the magic of bending would be the increase from the 100 to the 117. That's all bending is really doing. And there's a following of people that believe that to be true. And there's some logic and reason behind that. But still, you're left with 117 kips here and 17 kips here. And I don't know how you determine what the moment capacity is at a section that is out of equilibrium like that. It's anybody's guess. I believe that the concrete system, that the bending is so powerful, just the act of bending, that it will create equilibrium. Now I want to test that because I can't prove that. And that's the dilemma. That's where the headbutting was with all the people that I was discussing this with. Is I said I believe some mechanism develops that will put the system in equilibrium, and whether or not we have the pre-compression force, that will develop, and I think it's due to bending. Maybe a little bit of catenary effect, not the load balancing, don't ever say that, but I believe it has to, because the buildings, we would have a failure a week in California if that wasn't true. So any analysis that we do has to match reality. There have been load tests on existing buildings. None of them fail. Even though we know they're so cracked that there can't be any pre-compression, any significant pre-compression in the system, they still stand up. So something is happening. Some way, somehow, this develops. My theory that I'm putting forward is just bending itself can create that compression, and concrete is an amazing material, and it seems to move forces to where they need to be, increase them as necessary. It'll do everything in its power to resist that load and that moment until it can't, until it really does create a collapse. But boy, does it fight it tooth and nail all along the way. It'll do everything possible, moving forces, increasing them, putting them where they need to be, developing them in the first place. And I believe that happens. It's not an accident that post-tensioning is an absolutely best, most amazing system that there is. Okay. So, kind of restated everything I just said. I think that compressive force goes to 117. And I think it'll get there. Without testing, I can't prove it. Like I said, give me somebody else's money and I'm willing to put it where my mouth is. So this is just, as I sit here and think about these things. So how does that happen? We believe that the tension force will increase due to localized bending and strains. Okay, we all have to believe that, or if we don't believe in the FPS. Now, if that's a debate you want to have, that's a different debate for another time. But my point here is we believe that, which to me is the harder one to believe, and that strain is going to happen over a long, unbonded distance. You don't have high localized strains in post-tensioning. It's one of the greatest benefits of all time of them. The strain and stress increase distributes over a long distance because it's unbonded. Because it's unbonded, it won't create a localized high strain relative to the rest of itself. So this develops slowly during the bending. This, on the other hand, in my opinion, and again, we're back to just my opinion, develops very quickly, because that strain diagram it's happening right here. It's happening right as we're bending, at the localized bending place. So that compressive strain at the top of the concrete, it's not an unbonded strain. It's not developing over some wide berth of slab. It's happening right where we are looking. So that's going to build, in my mind, quickly. That compressive force will build up quickly to what it needs to be. This one is going from 100 to 117 very slowly. But I believe they will eventually get to equilibrium and resist, and this force moves up. I believe all the things that we say we already believe. Even in a restrained system, that's the difference. So anyway, I think I've beaten that to death. Bending causes compression. That's not a debatable thing in my mind. But boy, it certainly was when I tried to respond to people who I said, well, okay, so there's no pre-compression. There's still going to be compression. Oh no, there can't be. Cannot. So, well, we're going to have to agree to disagree. Okay, so here's the other point of the article, is that when universities are producing these terrific results that are kind of astronomical, and producing results that say the load capacity, the failure load capacity was some large multiple of the factored loads used to design the system, that's great. But how do I take that university vacuum of no restraint and relate it to my restrained buildings on the West Coast? What are we engineers out here on the West Coast supposed to do with that information? Believe it entirely that we will get the same load carrying capacity? No, we kind of know we can't. We have restraint. There's going to be some loss of strength, some penalty for being restrained. So how do I take these great test results of unrestrained systems and relate them to me, to my system? That's what was kind of inherent, and our really ultimate goal in this paper was to walk everybody to that point. Unfortunately, the vast majority of people who read the paper stopped on the first page and just couldn't get past it. So we really never got to what I wanted to get to. I'm going to throw a couple things out here. There's a lot of tested data. This was in 1971, University of Texas at Austin. Their tests of a flat plate, 2.9 times the factored design load. Wow, that's great. Another one, Virginia Tech. This was recently done. This was a terrific test. 1.5 times the factored loads that were used to design the system. So this is great news for everybody, particularly if you have completely unrestrained systems. This is great news for you. We have restrained systems. What do I do with this information? How much confidence can I have that my buildings will just have the 1.0? Well, that was kind of the point of the paper. Here's another one, University of Texas at Austin, 1985. Testing done. Failure load was more than the factored loads. I don't know what it was. This part wasn't published. But anyway, those are three examples of university testing that dramatically showed more capacity than the factored design loads used to design the test. So, okay, back to our article. And I think I've made it clear that I at least believe there's an increase, there's a compression force that's going to develop. We have to believe there's a mechanism, or we can't make the statement that restrained buildings are not severely compromised flexurally or in flexural strength or any other strength. We can't make that. So either you believe what PTI, Post-Tensioning Institute, publishes, or you don't. So if you believe it, then you must believe that there is a mechanism that develops when this never gets into the system. I mean, you can't believe both. You have to pick one and believe it. So back to the paper. This comes out of the paper. This is what we've spent some time on discussing right now. My point, and to get myself comfortable, was I want to look at this as an interaction diagram. That I don't think we get this precompression force multiplied by this arm in our California buildings. I think this is what the universities are getting in their testing. Again, a lot of people disagree with me. Lots of people disagree with me on that. I think the precompression force is an added force on top of the mechanism that's already going to develop. I may be, Brian, my dad, and I may be the only ones in the world that believe that. And that's fine. We're ready to test. I could be wrong, but one way or the other, no matter what your analysis is, no matter what your opinions are, they have to match with reality. They have to match with the fact that there's never been a post-tension concrete building that's failed that had perfectly healthy tendons in it that just had a lot of restraint. That's never happened to the best of anybody's knowledge. Load tests have proven that. So we have capacity. We're struggling to explain it. And I am too. But so back to this. My point was, if the University of any place is testing values and they're coming up here, I want to be able to subtract out the precompression force times the moment arm in their test. Get back to this, which what I believe on this interaction diagram is happening is they're testing here. I need to be comfortable that I can get here. I don't need the full value of what their test results are. I just have to be at 1.0, times the factored loads. And if this is true, if when you don't have precompression, if you believe you can develop this, then when you have precompression, this is another force. And that's the big debate. People said, no, that's not an external additional force. That's the same force and you've double counted it. Well, I'm saying when you don't have it and then you have it, it's in this picture or it's not in this picture. So I'm treating it, and I do believe that on top of the regular mechanism, which I actually believe is the primary moment resisting mechanism, if you are lucky enough in your system to get most of the precompression there, through the 120 feet all the way through the 150 feet, however long your building is to the midpoint, if you can get all that, that's great. But now I think you're going to approach what the laboratory testing tells you the strength is. For those of us who know that we're not going to get the precompression, we're not going to have it, we need to get comfortable that our system can work too, that we can take this double banded system that was tested at Virginia and use it in our systems and not lose sleep at night. So again, with my simple math that I'm doing, I take the test results, I subtract out the precompression force times the distance to half the slab. I still have a phi-mn greater than my mu, or m demand. Then I feel good about it. Then I feel comfortable. Then I feel confident that I can use that system in California and I'll still be here. They're testing here. I just need to be here. I don't need to be here, but I can't be less than this. So this was a method. Main reason that I wanted to, be the lead author on this particular paper was to show a relationship between restrained and unrestrained, and then to give us a confidence in California, for those of us who have restrained systems, that we can actually rely on that testing data. So, conclusion, we need to test these things. Can't prove it. It's difficult to prove. But there are some rabbit holes I think some people are going down of stating, and these are very smart people in very influential positions, writing me, sending me their free body diagrams, stating that we have zero flexural capacity if we don't have pre-compression. That can't be correct. It doesn't match reality. It doesn't match decades and decades of post-tension concrete buildings. It doesn't match load testing that's been done on these buildings. So we need to test. We need to take those same tests that were done and now restrain them and see what we get. Maybe I'm totally wrong. Maybe the relationship between one and the other is not going to be the pre-compressive force times the moment arm. I'm willing to be wrong, but we do need to know what it is. And secondly, we just need to be confident that our systems that used in a restrained system, because they're only going to get more restrained. The earthquake loads just keep going up. They never go down. And we just need to be confident. So that's the point. That was the point of the paper. Hopefully I've clarified some of the things that bothered people about the paper. And I will be presenting that paper at this same presentation that I'm giving you right now. They're not giving me this much time, so I drug this one out. But I will be presenting this at the ACI convention, the 320 meeting in Baltimore next month. So thank you for listening.